Welcome to the Houdini Masterclass on Vellum cloth. I will be picking up slightly where I left off, talking about how to drape a dress for Tommy, and look into some more character effects workflow questions about how to try and polish cloth to make it actually look nice. So the first thing we do is we start off with our previously draped Tommy cloth here, which I have outside of the Vellum drape node. And what often happens is, well, personally, I like to keep all the constraints live and use the constraints in Succeed in simulation. A lot of people instead want to just turn it into raw geometry and restart from scratch. So throw away any stiffnesses that have been set, any special attachments that have been set, and start with the geometry over again. The downside of this is you'll bake in all of these wrinkles and curves that you see in the dress. But actually, often people see that's actually a bright side because it helps preserve whatever you carefully draped in the first place by adding bend angles to preserve those particular angles. It also ensures there's no energy left in the system, where maybe it had to fight a bit in order to get these triangles short enough to fit where their final positions were. By resetting the dress simulation settings, you will have a nice fresh simulation with no energy to start with. So to try and isolate that, we first need to actually fuse stuff together, because this was welded together as multiple different panels. So we actually have unique points across these boundaries, which will make it annoying to try and preserve in the later stages. You can see here I actually didn't drape it very well. We've got some tangled geometry here that I should have draped better, but we'll work with what I have. The Vellum post-process is a great way to quickly weld things together. So by default, this will apply the welds, and this will ensure we have only one point along the seams. But you'll notice here that we suddenly have weird normal colors there. And you'll also notice that we have the back of the dress being blue and the front being white. This is because in the display options, there's now an option for displaying back-faced triangles, the opposite color. And that display option is on by default. And actually, at first I thought I wouldn't like it with cloth, because cloth you often see both sides of. But I found it's quite useful to know what the front side is and the back side is. But here, of course, I built the cloth of a couple of panels and welded them the opposite way around. So if I use a Poly Doctor, it has an option under topology to correct the winding of polygons to the majority. And this makes sure that we have a correctly, consistently wound system, so we don't have a contradiction of normals. But because there's just as many polygons facing one way as the other, it's just chance which one it decides will be out, and it decides to make the whole dress inside out. So a quick reverse swap will get us back to a good result. So I can use this as my initial conditions on a new simulation. And so this simulation, when we restart a simulation like this, there's some things to watch out for. One is to make sure there's no surprising ID attributes still around, because you might have used ID point attributes. And if you merge a bunch of pieces of geometry together, you might end up with duplicate IDs, and that will cause confusion and problems in the ensuing solve. The other thing to watch out for is there was a p-scale done when we correctly solved this in the Vellum drape world. So this actually has a p-scale set to it, which was set by the Vellum cloth nodes way up here-ish. By default, when I take the geometry and apply a new Vellum cloth to it, it will set the thickness again. And so if you're not careful, you might reset the thickness to the default 0.01, which might be too big for your geometry. So you might need to reset it here. You can also alternatively just turn off the thickness here, and I'll use whatever was coming in from the source. So from this, I can now run a simulation. I'm using default parameters. And if I do this with the default result, I will find I don't like the results at all. It looks pretty bad. And this happens even if you like the result of the draping step. One of the big differences between the Vellum solver and the Vellum drape is the Vellum drape by default runs at 1/5 speed. So this is equivalent of doing 5 substeps, but seeing every single substep. This is because often you want really fast feedback, so you don't want to spend the time waiting, seeing it in the correct real time, but you want it to be stiff and converge properly. So how do we find the correct settings to get this cloth to look more like cloth rather than this stretchy bag that it's doing right now? So what you basically need to do is, unfortunately, Vellum is topologically dependent. So the amount of stretchiness you need depends on how these points are connected together. So it's not possible to say that leather has this stiffness and linen has this stiffness and just type in nice presets. We'd really love to be able to do that, but we can't at the moment. So instead, you need to try some various wedges of different approaches to find out what settings work best. And that's what I've done here. So I built a quick wedge swap here. And so this is just a control interface, which I'm using to control what the active parameters are. And this lets me try a bunch of different things, changing the bend value, change the number of iterations, change the number of sub-steps, etc. And one of the important ones here is actually changing the skirt width. And so these are tied into different parts. So most of them are tied in the Vellum cloth. So for example, the compression stiffness and the stiffness are all controlled directly. Some are in the Vellum solver, such as sub-steps or the wind drag or the friction amount. And some, however, are actually up here, control the size of that base panel based on it for basically how tight that dress is at the bottom. So rather than running these simulations locally, I've actually done these on the farm and wedged out the results so I can play back the results directly. So the first step is to try and get realistic sub-steps and iteration counts. So in this case, the default sub-step 1 in 100 is way too stretchy and doesn't converge. And it's kind of important to point this out because we say we use XPBD, and one of the nice things about XPBD is you don't have to worry about doing too many sub-steps or too many iterations. The cloth will not become infinitely stiff as you do more iterations. This does not, however, mean that it will always solve completely. If you do too few iterations, it will stretch, or too few sub-steps. What I like about this graph is it also shows the difference between increasing sub-steps and increasing iterations. Namely, it's quite useful, especially with cloth, to probably go straight to 5 sub-steps, because that is probably the same number of iterations in total, but giving the solver a chance to work on a smaller time step really helps it resolve the energy in a more realistic fashion. What I've used for the ensuing examples is all sub-steps 5, iteration 200. So from that, we can move on to wedging another parameter. In this case, I'm wedging the size of that skirt. And this is actually when I first ran all these wedges, I didn't change the skirt size at all. And we had a lot of trouble trying to get the feet to move in a nice fashion. And the problem was that the size of the skirt at the bottom was actually almost smaller than the stride length of Tommy. And this meant that Tommy was really yanking the skirt apart when he took a big wide step forward. I mean, really, I guess you could claim that we should have animated a shorter stride if you're going to wear a skirt like this, but can't tell Tommy what to do. So if I make it even tighter, you can really see this come to a massive snap every time he moves forward. But if you increase the length, then the skirts all of a sudden can flow and get some more interesting behavior. This is something I've always sort of found is tailoring is so important for feeding back and to get the final look. It's like this, as important it is to get good numbers for your stiffnesses and bends and all those things. If your incoming tailoring doesn't move properly, the simulation can't get a good result. So we stuck with the 1.25 size skirt, and the next one is to deal with the shoulder straps. You can see they sort of float around, and this is partly because they're being lifted up from the rest of the body, so they're allowed to float around, but it also tends to be a result of the static coefficient being too low. The default is 0.5 here. If you could put it down to 0, you can see they really just slide back and forth, and if we increase it, we can see it starts sticking more to his body. After static, we can look at bend strength. So bend strength is what allows the individual triangles to bend with respect to each other. And it's important to note there's actually 2 parts to the bend strength. One is this bend strength that we're doing here, and the other is the compression stiffness. Because whenever you have a 3D network of triangles that's like not planar, the triangles themselves create a certain stiffness. Like if you've done any engineering, you know that triangular structure is actually a stiff structure that isn't able to bend. So if you make all those edges perfectly stiff, you can't get bending. But this is working in addition to that. So you can see here, obviously, putting it to 0, it's very small wrinkle sizes. And as we increase it, it starts having to have larger and larger areas there together. Ends up being more like a rubber mat when you go to the large amount. So we stuck with 0.1, which is actually the default. This is the compression that I started to allude to earlier. So if we change the compression, basically it allows these triangles to collapse but not expand. And so this thus prevents small micro wrinkles, because rather than having to fold over, the cloth can just compress in place. So you can see here that we've got a lot of very tight, crinkly detail when we have a very high compression stiffness, which causes it to create all these nuanced folds in the material, because it's forced to bend rather than be able to just compress in place. Whereas if we have the compression low, it can start to compress in place. So effectively, this is also showing this ends up being a stiffer fabric in some sense. For the next one, we try playing with air resistance. And so Tommy's actually moving forward in this example. So one important thing with cloth is to have some airfield present. If you try and do a flap and flag with no airfield, it just won't flap. It'll be very depressing. And so, but too much airfield, of course, and he's like moving through molasses or through water, and you can see the cloth just dragging behind him as a result. And so the 0.1 is the default. It actually we liked here. And the last sequence I did was with gravity, and 9.8 is of course the proper gravity for the scale geometry, but gravity really gives you sense of scale. It ties closely to speed, so if you change the gravity amount, it'll appear as if time is going faster or slower as well, is one way it ends up looking like, or a scale as well, where things seem bigger if you make them a lower gravity, because that's what it corresponds to. If we push gravity up, we'll probably see here we start getting stretching because we needed to change our substeps or our iterations to account for the fact that we have stronger forces in the system. So that covers how to try and get a simulation into a more interesting state by running lots of sims and starting to understand how these parameters affect each other and see what sort of ranges work well for your particular geometry. So the next one we're going to look at will be related to this, which is the question of targeting. So first I'm going to look at a simple piece of arm geometry. This is very much programmer art in this case. And to start with, I'm going to clear out this paint I had run earlier. So instead, just look at what happens if I take this bit of purple cloth and I bend it by placing it around a blue wireframe arm. You can see here we have, it's doing what it should do as cloth. Unfortunately, there's a problem in terms of art direction. You might want to keep the top of this cloth in place. And so one way you can do that is by selecting a bunch of points as pin constraints, but that's sort of using point selections, and I might want to have a 100% on, 100% off selection either. So what I can do is paint the input. And so I've created here an attribute angle to set a target weight attribute. This could be any attribute I prefer. And then use a paint sop here set to target weight. And if I enter the state of this paint sop, I'm able to now go and paint the values. So I'm going to actually set a weight of 1 just to pin the points along the top, like so. And then in the Vellum cloth node, you note I have no pin set. And instead use a separate Vellum constraints node. I set this to pin to target. And set the type to soft so I can see how strong it's going to be. And I set the strength to 1E10, but you notice I selected all the points. So I'm pinning every single point to the target. And so that will become a ridiculously strong pin, except I've also here said the stiffness attribute should use target weight. Now, the stiffness attribute does not simply multiply with the stiffness. If it did, a value of 0.1 times 1e to the 10 would be 1e to the 9 and still be infinitely strong stiffness. So it applies an actual exponential scale when it's applied. So 0.1 will actually become very weak, and 1 will be the full 1e10. So after this, if we run the solver, we'll see that we are indeed going to pin the top there. So the next problem I might have is I'm happy with the top being pinned, but I want sort of the wrist to be pinned as well, but not strongly pinned. I want to have it still be able to move and pull up. I want it to be snapped down and sort of keep near where it's supposed to be, rather than be able to fly completely fluidly like it is in this case. So to do that, I can simply paint a weaker pin here. And so I'll go back to the paint sop and change my strength to 0.1 and paint in, make sure I'm only displaying this one. I also have to cook the sim and it gets a bit slow. So here I'll just paint in the bottom. And the next question is what it's going to target. Because actually if I select this node here and hit play on it, you'll see that this torus isn't actually animated. So if I was to, which works fine for that top because the top was stationary, but this bottom I don't want to pin it to this original stationary place. If I do that, and I will do that by just resetting something that was set by hand here. So if I reset this to the default, which is first input, and we play this result forward, we're going to see that it is indeed trying to pin there, but it's desperately trying to pin back to that original location. So if I freeze it here and turn on the visualization of pin to target, we can see there's a whole bunch of points there saying, I need to pin back to my original location. That's just not what I want. I want to pin to this location on the arm, but I don't know where it is on the arm. So what I can do is instead animate the target. So this is often the case that if you have a cloth animation, for example, you usually can get a rigged cloth version of it, because either for a preview or just because the rig can capture it anyways, you can capture and deform the cloth with your rig. Sort of simulated that here. I've done a point deform off our arm, and so this is just a really poorly captured animation of the sleeve, not the actual arm itself, but this is the sleeve in question. And so I can use this animated sleeve as the target animation rather than the first input to the Vellum cloth. You do this in the Vellum solver. There's a choice in the advanced tab for what the target should be. Set it to a SOP path, point to this target node, and now it's going to try and target that animated version rather than the static version. And so thus we'll correctly anticipate where we want to actually be. So turn off the visualization of the pin to target. You can see here that it's not quite matching, but it's trying to match towards that because it's using a weak pin constraint. Again, I'll turn off the display there. And unlike before, it's not free to move wherever it wants at the end, but it's going to just keep the sleeve where I sort of keyframe animated it to be and let the rest bounce around as it feels like. I can use this targeting idea for more than just pinning to a one-to-one relationship, however. We can also use it to do resolution retargeting. So I'm currently just cooking 3 versions of the simulation. That's why it's running forward 36 frames right now. Okay, that's been cached. And now we're able to look at the 3 results. I'm going to first go through and look at them individually. Hopefully not reset the cache in the process. The first thing we have is we have a grid at the top. Hide everything else. And this is falling onto a rotating sphere. And so we run a simple Vellum solver on that, and we'll have the grid fall and rotate around. That's wonderful. But now let's say we like this animation, but we want to run it at a higher resolution. If you just subdivide the mesh as one way to get a higher resolution, and subdivide the ball to get a high resolution version of that, and then decide, okay, I'm going to run a Vellum cloth on the high res with that high res collider, and run this result, we will indeed get a high res simulation, but the simulation is going to have different results than we had in the low res version, mainly because there is more room for it to move. You're going to get different crinkles form. You're also going to get different levels of stretchiness or lack of stretchiness. It's going to bend tighter around the sphere because there's more ability to bend tighter around the sphere. And so you're going to get a different simulation out of it. But you might have been happy with what the low res did, and you just want more detail. You don't want to have a different gross behavior. So a solution to that is we can go and subdivide the low res version that we already simulated. We can subdivide that. And so this can become our target. And so this is sort of like a high-res version of it, but we want to be sort of like this, but not quite, because we want to deviate a little bit. So we time shift that to get the frame 1 version of it as a reference. And this we can also use as our target position, just like before, and we can paint it. So here I've painted the edges with a light, like 10% interest level. So just like before, we set up a Vellum pin to target, set the target weight to this. And now when we run this solve, we will see we get a behavior that is similar to the low-res version, but has the extra crinkles and stuff of the high-res version. But the position of these, the bottom edge is sort of matching the low-res version. So I've got here a display to show all 3 of them together. So we can see that the low-res version, we're seeing similar behavior here on these edges and timing on the edges. Not exactly the same because we're allowing it to deviate a bit, but we're getting basically the same set of folds. Whereas in high-res, it was doing something completely different at this point. This is useful if you need to match a silhouette or match the timing of something else that you got worked out in the low-res. It is important to note that you need to feather how this high to low-res goes in terms of this setting it, because if you make it too strong, it will basically end up matching that subdivided version exactly. And when you switch between them, it might suddenly have a bend or a crinkle there, which is, of course, not desired. So you want to sort of like use the smooth tool to feather off how these weights increase and decrease. While we're looking at attachment, we can look at attaching stuff to Tommy. Okay, so here I've, if I allow it to be seen, we have a cool superhero cape for Tommy, something a bit cooler than what I usually get him to wear. But let's look at how I built this up. There's an interesting point about reattaching that shows up with it. So first of all, I'm going to hide other geometry and just look at what I have here. I started off by drawing a curve for the general cape shape. And if I template the Tommy himself, we can see here that I tried to set the plane around the right location and then drew a couple circles around his head and his body, thinking something that looked relatively right. This I then resampled down to get a lightweight curve equivalent. And then I want these to become single polygons, so I used a fuse until increasing size until they finally matched, which in this case was pretty high of a fuse rate. Then I did some final tweaking. I do this after the fuse because then I don't have to worry about tweaking ahead of time, might change point counts or change the fuse amount. Here I've got my closed loops that I'm just using as my initial points. Throw another resample in to make them nicely rounded. I like how we can use the subdivision curves to do this. So there's an option here to do subdivision curves rather than just resampling straight or interpolating. Subdivision gives these nice smooth results from my jagged programmer choices of points. One trouble though is this will unique the points. And so after running the subdivision curve option, you're going to get duplicate points here, somewhere around here-ish. You'll see a duplicate there. There's one somewhere on this curve. And so I want to fuse it again to make sure these are closed loops. That's because planar patch from curves, which is closed loops to be able to tell where to generate them. So if I run planar patch from curves, you know it's a problem. Namely, I want a hole where his head is, but this doesn't seem to have done it. But if you look very carefully, you can see that planar patch from curves does properly preserve that internal boundary. There is a loop of points that represents it. But how can I separate off that inside from that outside? Well, to start with, I'm going to go through and first just make sure I've got them all numbered. This is because I want to be able to correspond points properly. And then I switched to extract centroid. And extract centroid allows me to break up by each piece, so in this case each index. And this basically gives each polygon its own unique number, and then each polygon gets its own unique point from this. This sort of computes a dual, as it's called, very effectively. So I've got 1 point per primitive, and that point is in the middle of the primitive. The advantage of that is we have a new SOP called the winding number SOP. This is rather complicated SOP in some sense, but it's really useful for doing this inside-outside tests. In particular, I can tell it to run in 2D, and given a curve network, which I have up here, tell me how many times that point is inside of that curve network. And so given these points here, it will compute this winding number for each of them. And if I do the info guy for this, and then middle click or click on winding number, it will color by winding number. And you can see we definitely have a difference of winding number for the ones inside and the outside. So in this case, I can delete all the ones whose winding number is greater than 1.5, and that will immediately select out what I want from my set. Then, of course, I find out, as inevitably the case, I actually have it intersecting his shoulders at this point, so I need to bump it up a little bit in order to create a valid initial cape configuration. So all that, let's turn it into cloth, and let's use a drape SOP and say, yep, we've got a nice initial drape here. We're happy. But one problem is if I disable this attachment here, instead go straight to a solve, and we're now going to solve this cape on a slightly different Tommy. This Tommy is fallen downwards, and so the cape will quickly fall off his head. You can see it falls off his head in a most embarrassing fashion. So what you usually have to do with superhero capes is you need to glue them to the actor to make sure they don't move around too much, or apply some pins to them. You don't want to do pins in this case because he doesn't have any clothes underneath, so it'd be right on his skin, and that'd be very painful. So I recommend glue instead. So the attach here is how we can do that. This attaches to the gray input, and I selected the points here. We can see which ones I selected. If I clicked at this, I selected them right along the front here, and I gave them a lower stiffness, so like a weak 1000 stiffness there. And they're told to constrain to the closest location on the primitive. So they'll basically find where they are on that primitive and stick themselves to that distance above the primitive. It's important to note if this was a distance away from the primitive, they'll preserve that distance, but not that distance in the normal direction. So they'll still like rotate around that constrained location. They don't latch themselves onto that normal location. In this case, that works. I've now got a Tommy attachment, which is going to, if I move my camera with it, keep the neck intact, so it's not allowed to come fully off. So that's great. I'm happy. I've tested this out, and I want to send this rig to someone else. So let's use a Vellum pack. This will take this geometry along with all the constraints and bring it into a single geometry. I can time shift that to make it not time dependent, so it's just living on frame 1. Then let's unpack it later. Maybe we load it from disk. This is a totally different file or something. And I'll go down here and I will ignore this node here. And instead, I'll just tell it to collide with this one. But this new one has a slightly different animation. This one is flying to the side rather than down. But if I play back this, I'm going to get a very surprising result. Namely, the neckline is not being pinned to my move in geometry to the right. It's being pinned in a totally different direction. And if I display the visualize and display pinned to target, attached to geometry is what this one is. Get it right one of these days. We'll see that it's actually attaching way down here. And this is because the saved geometry stores the SOP it's supposed to attach to. It doesn't store that it wants to attach to the rightmost input, so it doesn't get overridden when we run this new Vellum solver. This is a good thing because you can use multiple Vellum attaches to attach to different things, but it can be very surprising in cases like this where you expect it to attach to my new geometry. The advantage is all this information is being stored as normal geometry. So if I go to the null and go to a geometry spreadsheet for this, we can see that there is a option on it for target path. And so I scroll to the bottom, we'll see, yes, there's all these people there saying I need to attach to obj cape transform 2. And that comes from up here. They basically stole this node name and recorded that that's what they should attach to. I don't want them to attach that anymore, though. I want them to attach this node. So I can use attrib string edit. And so this lets me just change whatever ends with transform 2 with something that ends with attach. And after that operation, we should see the attachment now correctly following the new geometry. So usually this sort of replacement can be done with an attrib string edit, just to update the new node names. But if you have like a particular rig, you might even get away with always using the same named node. Because if you have the same path and name to it, it will just rediscover the node and appear to work without any changes. But it's important to be aware of it for the cases where it doesn't work. While looking at stuff that doesn't work, I think I should also at this point look into one problem that can occur, which is bouncing cloth. One of the important physical properties of cloth is that if you take a big chunk of cloth, such as this one here, and we drop it on this cube, is it won't bounce. But here, you see it does bounce. And so this is very distressing when it happens because we naturally don't want that. If you're looking for the bounce settings in the Vellum solver or Vellum object, or the bounce settings in the whole system, you won't find any because PBD really doesn't have bounce because it's not able to bounce. But that's clearly a lie where I'm seeing it bounce here. Where is this bounce coming from? This bounce is being triggered by the second order integration method. So this is a way to predict how the cloth is moving over time. And if it predicts properly, we're able to greatly reduce the number of constraints required to solve and improve the liveliness of the simulation. But when it predicts poorly, we end up with exactly this sort of ridiculous bounce. What we've done in later versions is we've actually improved this. So hopefully this default setting won't bounce for you right now, but you might still end up with bounce depending on your settings. So it's important to know how to fix it if you do see it. So the worst way to fix it is there's an option in the advanced integration to go second order or first order. So if I switch it to first order and hit play, we'll see it properly not bounce. But as I'll show in the next file, that's not something you want to just do by default because you lose a lot of energy and a lot of potential stretchiness. What you need to do instead is adjust the max acceleration. And so here we have an option on the node for max acceleration. The default used to be 100. That was a bit too conservative. We've changed the default in later versions. After the first production build, it'll default to 30. And with that, this particular case doesn't bounce. And so I can actually show the fall off amount. So here I'm coloring it based on whether or not fall off occurs. And so if I go forward, we can see in this one particular frame, it turns white. This means that the solver has detected that the collision has resulted in more than 3 gravities of acceleration. And so this means that the second order prediction is going to be wrong. And so it switches back to first order integration at this point and thus avoids the bounce. But it's using the second order integration all the other times and thereby getting the nice properties that we want out of second order. But I really don't want you just believe in second order just because I say so, and I definitely don't want to just switch into first order because you don't want to deal with occasional bounciness. So I have an example here just to show why first versus second order is important. So these are two identical pieces of cloth. The big difference is one is at the default second order integration, and one is at the first order integration. So if I hit play here, we can see quickly enough there's a difference between the two. So to show which one's which, I'll display this one here, and we can see this is the first order, and we can see it's very stretchy compared to the second order because it wasn't able to predict this sort of swinging pendulum motion that often happens with cloth. And as a result, the constraint iteration had to keep fighting to pull the points up and isn't as effective. Here it has less work to do because it correctly predicted it. The other thing is this results in damping, in other words, a loss of energy. So we can see that the second order one's a lot livelier and more interesting in how it's simulated, whereas this one is just more viscous and it's lost more energy, even though they both have the same air resistance and same other properties. Another thing we commonly face is, of course, getting strange movement into our simulations. We often don't have control over what we're asked to put cloth on top of, and while we'd like it to always be nice, realistic behavior, often it isn't, and we need to have ways to deal with that. So in this case, I have my same dress as before, and I, however, have a body geometry here, which has got a very fast movement associated with it. So it's going to jerk very quickly over to the right and then stop. So to make this more obvious, I have here a default Vellum solver, except the big difference is I changed the wind force to wind drag to 10 to make the wind more apparent. And so if we hit play forward here, we'll see as soon as Tommy starts flying to the side, that the incredibly strong wind is something that really holds the cloth back, and we get this horrible stretching, and it's a lot of work to try and get this. I mean, this might be realistic for how quickly he is moving inside this thick atmosphere that we've set up, but it might be you don't care what's realistic. You just want it to, have just this same amount of wind drag when he's still, because you like that, but when he's moving, you just want him to move less, but you want to move the same distance. So one solution is to change the wind force dynamically. In other words, speed up the wind to always be the sort of same speed that Tommy's moving in. Sort of make it relativistic to Tommy's frame of reference is another way of looking at it. So we can do that. We first decide what we want to make it relative to. So you might have had, for example, captured deformed version of this cloth that you could use as the relative frame, or sometimes the collision object, or maybe there's a camera you can use as the relative frame. But whatever it is, you can use the same technique. So I start off with this body. I get a reference version of it at frame 1, and then I run extract transform. An extract transform lets you just get the rigid position that best matches. So provided the point counts and point order stays the same, this could be a deforming geometry and it will still not be confused and find the best transform that works with it. Given this single point that you can see at the center, I can use a point velocity to compute what the speed of that point is at any particular frame. And so then this point velocity, I just made a null stop where I just read off the point velocity. This just lets me see it and do channel references easily. Like maybe I want to have a scaled version of this. But I can go to the Vellum solver and set my wind speed to refer to that compute wind speed. And now when I display the correct solution, we'll see that the wind speed of this simulation will roughly match the speed of Tommy himself, and so we'll get no actual sudden jerk from the wind. Now we're still getting acceleration here because Tommy is hitting and dragging the cloth, and it has its own inertia where it's not necessarily responding to the wind right away, but we've been able to cancel out most of the wind caused by his motion and still get some light effect from it. You can also scale this, obviously, because you don't need to use 100% of it, or do something like use only one dimension. Like maybe there's some Y motion that's detected, but you don't want any Y in the resultant wind speed because that might cause the skirt to rise or lower. So you could just set that to 0 and ignore whatever the computed amount is. Now, in addition to the wind speed, there's another component to this, which is the collision component. So I still have Tommy actually hitting the side of that because he's actually moving quickly to the side. And this is might not be something you can get rid of using just wind speed type hacks. So here I've reduced the wind drag back to 0.1, so it's not having too much of an effect directly. And instead what I'm going to do is look at what happens by changing the frame of reference entirely. So first I'll switch it back to doing the raw solve so we can see what that is using a zero wind world. So I don't have a wind force of 10 here, I have a wind drag of 0.1. So it's going to be less. This is mostly all coming from the inertia of the cloth not wanting to move to the side quickly and just the collision of the leg against the side. So you can see we get that massive yank jerk to the side. Alternatively, I can say I want to reframe my reference down to a new world. And I can do this by starting with whatever I'm going to use as my frame of reference, doing the same extract transform as before, which gives me this animated point. But then I can do a simple SOP solver to find out a new position over time. But this one I'm going to clamp what the maximum acceleration is at any particular point. And I've done this with this pair of nodes here that can be done just cut and pasted for your own use. And you note that there's max acceleration parameter I promoted. So the idea of this is first I store my original position of this thing as old pause and initial pause. And then inside the solver, if I dive in here, I've got my previous frame and I've got my new animated position. And so my new animated position I can compare against the old true position it had. And from that I can compute a velocity of that object at that time. And then I can compute a acceleration that refers to. And then I can do a clamp of that acceleration with our actual maximum acceleration that we've got as a parameter, and then reintegrate back the velocity in the position to create a new actual position to output. So what this looks like is if I look at just this single point, we're going to see it now lags behind Tommy himself. It still moves with him, it just moves slower because it clamped at 10 acceleration. If I do, so 1 acceleration, if I do 10 acceleration, it can move faster, but not move it because I guess he has around 20 acceleration. If I unclamp the acceleration, make it very high, we're going to get something that just matches it precisely. And so this way I can control what's the maximum acceleration my cloth will experience from collisions using this. So setting it back down to 1 means I'll still see a jerk to the side, but a very small movement to the side. So let's make this like 3. So we have only small motion. Now I can then do apply data, and this apply data here will just subtract the difference between the two worlds from every point. So this causes my collision object to move this smaller amount. And because the Vellum solver isn't caring about velocities on the collision object, I don't have to recompute those. I can just move the points and get the right result. So here I have a matched wind version. So like before, this is just grabbing the point velocity of that computed damped position. So the wind is in the same space as Tommy. But otherwise it's got the same motion. So here we're going to see it move, but it's going to move only a small amount because of the clamped acceleration. You can see here in gray, that's the actual collision geometry, which is of course moving a lot faster. But the blue is the collision geometry, which the Vellum solver is seeing, which moves slowly, letting us get this slight push to the side, but not the huge push we'd get if we moved the official distance. And I can do the opposite of the add delta to remove the delta. And I do this to my resultant Vellum object. You can see it quickly flies off to the side. Now it's been put back in the correct space. And so I'm seeing what I should see in the end. Now, of course, at this point, all the velocities that Vellum computed will be wrong because they were done in this earlier space. And so it's important to do a point velocity to recompute the actual velocities from how it actually moved in the end, because that will change. Continuing this idea of getting bad initial geometry, quite often you might get stuff like this, where you've got a piece of cloth and a collision object, but the cloth is already colliding the collision object on your first frame. And so if I animate this, we'll see that Vellum will basically trap those points inside because it doesn't know that they're on the wrong side. And so you'll end up getting stuck inside and it's not able to actually pull it out. Ideally, of course, you could push this out through some operation and get on the correct side. Maybe you've got an STF and can push it out from that. But alternatively, what you can also do is do this approach. I can group the points that are inside, in this case by using an inside test, and then disable external collision value set. I'll set it originally to a value of 1, And this is what's usually done if you don't want points to collide with external objects. So I've put sort of a virtual hole in my cloth here. And if I run this, we should see the cloth is now able to slide out. One problem, though, is you can see that even though it slid out, it gets to fall back in again. And so we sort of got this permanent hole in our object that we don't want. We want those to be opened up when they get resolved. Now, fortunately, Vellum has a way to automatically resolve external collisions that are now correct. What we need to do is tell it disable external of 2. 2 tells it that this is an automated disable, and so as soon as these points become untangled, it will re-enable them again. And so in this case, as soon as they're free up, you can see they turn off, and that way when it falls back down, there's no longer a hole in my cloth. As soon as it gets pulled out, it works. Similar to that idea is this one, where we have basically a rock in a hard place. So we've got a piece of cloth, and we have a sphere and a torus, and we have the torus come down and crush the cloth and go right through, and then leave again. And so when it crushes the cloth, Vellum is smart enough, yay, to mark those points as disabled. Namely, they weren't able to handle external collisions properly, so they're now turned off. But there's nothing currently restoring them to the correct side of this collision. And so they stay on the wrong side and just sort of float there, and we don't get them resolved over time. What you can do in cases like this is double up the collisions. So the sphere is currently added as a static object, but it was created using the static object tool, so it has both a VDB and a non-VDB collision associated with it. And by default, the collisions is set to use solver default. And for Vellum, this means to basically use surface collisions. But here I could just cut and paste this node twice, and this new copy of it is also set to volume sample from the VDB, but I changed it to use volume collisions. So this will force it to use volume collisions for this one. So if I use both, we basically can have the surface collisions of the sphere properly keep all these sharp points, but the SDF collisions can ensure we can restore the correct size. So if we run this forward, we'll see the torus crushes it, they turn yellow, but when they come back up again, most of them are able to be restored and end up on the correct side. The downside of this, of course, is you have to build an SDF every frame, which is very annoying if you have animated characters, but it might be important. You can thus have the surface collisions handle basically all the sharp fingers and other bits that SDFs can't handle well, but a low-res SDF can sort of keep stuff outside where necessary. So in this case, this is the arm that we've seen earlier, except I've decided to up the ante and add a few more layers of cloth around it. So I've got quite a few layers of cloth here. And I'm going to disable this by default here, so we can see what happens with no, and reset this. So this is now back to pretty much the default values for this operation. So if I hit play, we're going to see the red circles here where self-intersections fail. You can see if we start to have a bunch right where it hit here, it couldn't resolve them. And similarly at the back, it starts failing a lot very quickly. Start seeing the other color poke through, which is not desired. So the first rule to resolve this sort of problem is to have more post-collision passes. In particular, it's the rough rule of thumb is 3 plus the number of layers. So here I can switch to 8 passes. And these extra passes are a lot cheaper than you expect them to be. They're a lot cheaper than full collision passes are because they only apply to the points that are actually failing the collision. But it helps the system better resolve these things that might need multiple passes to get to. So here the back is doing much better than was before, and as is the front, but it's still failing more than I would like. The next level is to give the solver a hint. And so the problem is it acts as sort of like a unbiased system where each of these layers is trying to get out of the way of the other layers, but really there's a certain order it must be resolved in. The layer on the top, if it doesn't move out of the way, the ones underneath have nothing they can do. So it's important that it's made sort of lighter than the ones underneath so that it knows that it should move out of the way more than they should. But you don't want to make it too light because obviously then it'll become just a one-way interaction where you just simulate one layer, then simulate a layer on top and a layer on top of that. So you can get a combination between the two worlds using the layer shock ability. To enable this, all you have to do is have a point attribute called layer, which is an integer. And the higher the layer number is, the sort of lighter it will be. but the lightness is only dependent on the difference of the layers, so not the magnitude of the difference, but just one being bigger than the other. So if I have layer 2 and layer 5, layer 5 will act to be 4 times lighter because I've got layer shock of 4. If I have layer 2 and layer 100, it will still be only 4 times lighter. So I'll add back this copy num attribute, which creates a layer attribute. And so with this, hopefully I will get less self-collision failures as it's able to resolve them in order. In this corner here, I'll still get a fair bit because it gets very crinkled up here. But hopefully the outer layer ends up resetting correctly at the end. In particular, you can see the outer arm is kept the same and succeeded, as has this leading edge. So for this example, I'm going to look at another problem that can come in with your incoming animation. So to motivate this, I'm going to start with this geometry here. And so this is a simulation that we've theoretically been given, and it's a walk cycle. But there's something wrong with the walk cycle, namely this arm is going, not only is the thumb cutting right through the thigh, but this arm up here, the flab of the arm is hitting right against the chest, and this leaves absolutely no space for cloth to be. So there's no hope for a cloth solver here. It will have to start disabling stuff. I mean, Vellum will try its best, but it's way happier in the world if you can put a gap in there somehow. So ideally, you could send it back to the rigging department and they would invent some way that makes it all gap-free, or send it back to animators and ask them not to be gap-free, but you might not have that luxury and you need to just somehow break open this part. So what I've done here is I've isolated just part of this geometry just to make things faster. And then I went and decided, just like before, to create a pin attribute. And I painted the pin attribute. And so the idea here is I want all these red areas to be preserved exactly, and the green is where I'm allowing it to have some give. So I'm like, I don't particularly care about the position of those points. And it's important to note the position of these points are not your final render points. This is just going to drive the collision geometry of the Vellum cloth solve. The actual render geometry will be the original geometry. So any flex or whatnot I got in this will not show up in that. So having selected those ones, I can then go and make some Vellum constraints. So I'm going to switch back to frame 1 here. And we make a cloth setup of the whole thing. And I set soft pins set to match to animation is important here. And I set this for everything whose pin value is strictly less than 1. So this avoids creating pins for all these purely red points. I do this because I have a stiffness of only 10,000 I'm using. And so I'm varying basically the stiffness of this area using that fall off idea. Then for the hard pins, I set everything that has a pin of 1 that was painted full red to be a hard constraint. So first off, I'm just running this with a soft match animation, just as a didactic example. So let's see what happens when we solve this version. So the idea here is the strong pin constraints will thus be exactly enforced because they've got a 1E10 strength, but the soft ones will be able to flab around and get out of the way. And this is the key point here. Let's see, we're starting to get the collision resolved. Yeah, so if I dive in here, we should see, there we go. Good. I was afraid I wasn't showing what I wanted to point out. So as the hand came in here, it hit the really strong pin constraint, so it deformed out of the way, which is what we want. However, you can see it also dragged those hard pin constraints over. This is because 1E10 isn't infinity, and so these points are still able to move, and in particular, collisions tend to trump the actual pin constraints themselves. So if you want something perfectly pinned despite collisions, you have to do more than just set a very high value on a soft pin. You want to actually set a hard pin. So I'm going to go back and reset it now, and we're going to do it with a actual hard pin constraint. So I'm going to do it as permanent in this case because I don't want to reactivate it. It's more efficient to do it permanently. But again, we want to make sure we have matched animation turned on. And now when I hit play, and now when we zoom in, hopefully we will see more of a sensible behavior. Well, we don't have any motion on the other points. Now I still have that hand getting trapped on there, which is not good because we're getting really bogus collision geometry. And this is, again, due to substeps being too aggressively low. So if I rerun the simulation with say 5 substeps, notice it's slower, but it's not quite 5 times slower, which is always nice. And as the arm comes in, we should get a better collision geometry this time. You can see here it slid out of the way, thus leaving a gap for any potential pants to fit. Though really, in some ways, I just want to chop off the hands in this case. I mean, more practical is probably what it did over with the inner arm, where it leaves a gap between the torso and the inner arm, allowing the shirt to fold over in there and obey both sets of constraints without having to disable. So thank you very much for joining me for this masterclass on cloth, and I look forward to seeing what cool things can be done with Vellum. So thank you very much.